Just want to do a quick thank you to Derek, Colin, Ginger, and all you folks at Synadia for letting us come in and talk with you guys a little bit about what we're doing on the power grid and what some of the things that Duke Energy is looking at from the future standpoint and how things are going to work and differently than what we do today. So I appreciate the chance to come on. So let me just go ahead and jump in here just a little bit. That's me. Just a little bit of background on me. I've been with power company. I've been with Duke Energy for a little over 23 years now. I've done everything from programming COBOL on mainframes, which is kind of a little bit of a hot topic these days with everything that's going on. But all the way, through Java into, I haven't done embedded stuff. I'm not a UI person. I'm done Java, a lot of behind the scenes kind of things. So I like to build things. I like to figure out what kind of things that are coming down the pipe that we can wind up using in our space. I have a wife, 7 kids, 3 dogs, and a cat, and all of us being at home. Thank goodness there are only 3 of the kids at home right now, or I'm not losing my mind a little bit. But what I'm going to go through today is I'm going to give just a little bit of quick background on who Duke Energy is, how the traditional power grid works, and how we are seeing how we envision that working differently in the future, and a lot of the reasons why, and some of the new standards that our group is helping to build and develop and push forward, and most importantly, to tie back into how we're actually using NATS inside of a microgrid that we have built today. So a little bit about Duke, a couple of quick facts. The one big takeaway that you can take out of this is Duke Energy has been around for 150 years, give or take a little bit, and a lot of that has come through mergers of multiple utilities over time. You can see we have customers from Florida all the way through Indiana. We do electric, we do generation, distribution, transmission. We also have natural gas distribution in several states as well. So we're kind of spread out, and this is really our regulated service territories that you see here. But if you look here, we have things going across 22 different states where we have a lot of renewable energy generation. We have energy storage projects. So we're doing a lot of things, in our non-regulated space where we're, figuring out how to make some of these new technologies work from an electric power distribution standpoint, and how we can utilize those things going forward to, get off of some of our older, generation technologies that we actually have. Just a quick little bit about how the traditional power system typically works. You typically start with some large-scale generation source. In this particular slide, you see it's a hydro plant where release the water, you turn the turbines, you generate electricity. Well, coming out of the turbine or coming out of the plant is you wind up sending that across distribution, and you send it across transmission lines. Excuse me. You send it across transmission at very, very high voltages. You can see that some of our transmission lines go up to 500,000 volts. So it's extremely a whole lot of power that we're sending across through there. Well, it makes its way down to transmission substations. Transmission substations wind up splitting that out and sending it in several different directions, typically dropping the voltage down so that it goes to distribution substations. The distribution substations at that point, they drop the voltage down even lower, and then they start spreading that power out across many feeders coming out of a substation. And the feeders are the typical things that you see, your power lines running in your neighborhood, the underground service that maybe in your neighborhood, if that's how it's laid out in your particular neighborhood, that winds up going to your houses. And you see that this is traditionally been one of those one-way power flows that going from generation through transmission through distribution to your house, and that's how it's kind of worked for the past 100 years or so. But what's really come in and changing things up, well, okay, let me talk about this just a little bit. All of those systems that we have back on this slide where we, have the components that are in the substations, we have the components that are on the feeders. In today's world, those are, managed with SCADA products, the supervisory control and data acquisition products. Inside of our back office operations center, you wind up seeing these massive, screens, all these huge systems with, managing things on the power grid from a very centralized standpoint. That means that these systems, they reach out to all of these components across the power grid, pull the data back in to these centralized systems, run computations, run power flows, and figure out what new settings need to be sent back to devices on the grid, and turn around and send those back out. It's very central managed today, but one of the things that we're seeing as we get a higher and higher penetration of, solar and these distributed energy resources, that these kind of systems are not going to work very optimally going in the future. Also today, in some of our SCADA systems, we have a lot of siloed systems that we wind up, traditionally we have put devices out in the field where they serve kind of a single purpose. They have, one way of talking to them. They have one way of communicating back to some piece of software that we have in our central office that winds up kind of decrypting those and opening up the data at that, so that we can pass it across enterprise service buses in the back office to do some of those integration kind of things. But everything is really kind of very proprietary and very siloed as far as our systems are concerned today. But one of the things that we want to be able to do going forward is, I'm going to skip past this slide. One of the things that we want to do going forward is we want to take those same kind of devices that are in all these proprietary and these siloed systems, and instead of having to pull all of that data back into central office systems, we want to distribute compute resources out at the edge of the electric grid. Today, we've got a lot of devices out there that may have the horsepower and may have, the underpinnings of being able to do it, but they have never been set up to have those capabilities of running applications right next to these devices in the electric grid. So we have been working on, this whole concept of distributing nodes out in the field, or replacing some of our existing communication equipment with these nodes, so that we can run applications right next to these devices on the power grid. One of the things that you see referenced here is the open message bus. That's a standard that we have helped develop, inside of Duke Energy, and got it actually ratified as a standard for the North American Energy Standards Board, so that other utilities can pick up and use the same kind of concept that we've put out here, so that they can build systems as well. And this is where, and today we're kind of envisioning NATS is our, way of doing the publish and subscribe, that we can have the devices tell us what the data is, instead of these centralized systems having to reach out and poll these devices all the time. We're kind of flipping it upside down a little bit and having the devices tell us what the current state is, and also that they're listening for control messages that may be published going back to them. Now, with that being said, we can't really cut off our back office systems. So we still want those to be able to get the data that they need to pull off, the functions that they're built for. So we envision those kind of devices, instead of being, having the direct connection all the way to the end device, is they wind up becoming clients of the field message buses, and being able to pull the data all the way back in and pull off what they need to do. Once we get that kind of setup, then it allows us to do things about like this. So consider that we have, a solar energy farm that's, randomly, depending on the time of day, depending on clouds, is generating power. But we also have an energy storage system there. Traditionally, both of those devices would be pulled from centralized systems. and would turn around and send control messages like back to the battery to tell it what to do based off of what the solar is doing at any one point. Well, that is not the most efficient way in the world of doing it. So what we want to do is we want to put that node out there. We want the node to be listening to how much energy is being produced from the solar. We want to immediately, depending on if we have a rapid swing, say clouds come over and we don't have the solar generation anymore, we want to tell the battery to kick in to compensate that. Well, we can do that basically immediately with distributed applications in the field, but we can still pass that data up back into the central office. And this is something that we proved out a concept like this about 6 years ago, where we were able to take a 1 megawatt solar farm, a 500 kW battery, and between the two of them communicate in like 250 milliseconds. We were controlling the battery to tell it to compensate based off of the solar, even little small dips in the solar that the battery could dispense energy, or if there was too much solar based off of the curve that we wanted the power generation to look like, the battery could actually absorb some of that power and save it for later as well. So one of the things that we've always done in the past is, we've never really had a good place to test some of the things that we're wanting to do. We've tested a lot of new equipment on live feeders with live customers, and testing out new equipment, things don't always work exactly the way that you would like them to work. So we started back in 2014. We started building a microgrid lab. We took over an old training facility that Duke Energy used to have, and we have implemented a microgrid at this location where we can actually disconnect from the power grid. We have our own internal networks so that we can test things that are not going to affect any customers. We can put in new products. We can see how they work, but it's also given us that ability to be able to test how to build a microgrid, how to mix and match components to build different styles of microgrids. So just to dive in just a little bit about some of the kind of equipment that we're dealing with here. And this kind of gets back to Derek's point about, don't think about IoT being, little tiny devices somewhere. These are very big, very expensive pieces of equipment, but we're kind of treating them as that same, IoT mentality, where we've got a 150 kW solar farm up here, just around the corner there. You can't hardly see it, but there is a small energy storage battery that's connected on the DC bus up there. And we have a couple of different generators over here. We have I believe it's a 360 kilowatt natural gas generator. We have a couple of 65 kilowatt microturbines that's run by natural gas as well. Just an interesting fact about those is when they start up, that there is an actual stage in the startup that's called liftoff, and they actually sound about like jet engines, especially when you cut them off. You can hear them wind down, which is kind of cool. But we also have a 500 or 650 kilowatt battery over here. That's what you see in this shipping container. That it's a 650 kilowatt peak energy storage battery that we can use to drive this microgrid. And when we disconnect from the grid, this battery right here, quote, becomes the grid for the rest of the facility. We have other things here. We have a whole bank of meters that traditionally we haven't really trusted a lot of the meter readings that come from device. Like all these devices, they can actually give us, measurements of what they think, the amps, the volts, the watts and stuff is coming through those devices, but we haven't traditionally trusted them to be highly accurate. So a lot of times we put in an extra high quality meter there to measure what the exact power output and input on those devices are. We also have a local weather station that's right here. You can't see it very well in that picture, so that we can have kind of real time weather updates. There's also another weather station that's up here at the solar farm as well, so that we can get those real time updates. We have a load bank here, and what it essentially is, it's like a big hair dryer, if you will. It actually burns electricity is what its point is. And the reason that we needed that is we needed the ability to simulate higher loads. The lab that you see over here, even on a big day of actually pulling power into the lab, we may pull in 40, 45 kilowatts of power. So we can't really simulate large scale loads. So we use this controllable load bank so that we can have it actually use up to 500 kilowatts of power at any one point. So we can turn it on and actually simulate some of those loads. This the islanding switch here, this box is what we actually use for disconnecting and reconnecting back to the grid. So it is a highly important component for us. So, when we disconnect from the grid, we still run all of this equipment based off of the components that you see here, and being able to generate power, keep smooth, clean power for the rest of the devices. And also inside the lab, it actually drives the power in the lab. As you can see here, one of the things that we're doing is, instead of having a centralized application, poll and control all these devices, we are actually spreading around our OpenFMB nodes and using a NATS message bus with these devices. We have applications that are distributed around the different components in our microgrid. They're all publishing into, right now, a single NATS server, but we are getting ready to push NATS out to every one of these nodes with some of the stuff that you'll see from Wally later with his new Helm chart and stuff for NATS, that we're getting ready to start pushing individual NATS brokers across every one of these devices in our lab or in our microgrid. So that's coming within the next couple of weeks. We're also going to be putting distributed applications for controlling this microgrid. And how it stands today is we're really just getting kind of telemetry, the measurements, the status, and things like that coming back from all these devices in the grid. So we're getting ready to layer in a distributed control for all of these devices. That should be coming here in the next couple of weeks. Here you can see we're using Kubernetes and Rancher to distribute the applications across all of these nodes in our setup. Here you can actually see kind of a list of some of those applications that are talking to all these devices in our microgrid. You can see that we've got some applications in this list that are C++. We have some that are Go. Been working a lot lately with Rust, so I'm very much looking forward to Tyler's new Rust client. Been playing with that a good bit. So our view is definitely looking at some of those tightly compiled languages that produce those small secure applications that we can distribute across the power grid. Now, going back to a couple of slides back, you saw the little green dots that we had in our microgrid. This is kind of a scaled down picture of it, but this shows how the microgrid connects into the feeder coming out of our substation. You can see that up at the substation here, transmission comes in, voltages get stepped down. There's circuit breakers on every one of those feeders to prevent faults. But we have a fairly large scale energy storage system that's basically right outside the substation. There's up near the head of the feeder, there's a lot of loads. We have reclosers, which is just a fancy kind of switch that's in the middle. So if there's faults down here, that this recloser can open up and power can still be run up here. We have reclosers in front of the microgrid as a protection kind of device. So if if the feeder sees something going wrong with the microgrid that it shouldn't be doing, that this recloser can open and kind of island the microgrid away from the feeder. We also, over at right near the end of the feeder, there's a 1.2 megawatt solar farm that's on top of an actual manufacturing plant that's right near our microgrid. So we've got devices over there as well. But inside the microgrid, we've got all of our pub sub stuff going on with NATS. But one of the things that we're getting ready to do, hopefully in the later part of this year, we're starting to make plans for it if we can ever actually get back to real working conditions, is we're going to take that same concept of use and publish and subscribe across the microgrid to where we're going to take the publish and subscribe to a feeder level. We're going to basically move up one level, and we're going to have a message bus of all of those major components across the feeder talking with each other. Right now, we're not going down to like a residential home. We're not going down to that layer of getting data back. So, we're trying to stick to those larger components that are on the grid to help balance the feeder out. Eventually, our whole concept is to be able to take some of this all the way down to, maybe the transformer or the meter on your house, so that we can have, get more real-time kind of data coming back into these systems and be able to share that data amongst applications that's on the feeder. But with this picture, one of the things that's kind of missing here is, we got one bus at the feeder. We have a different message bus that's inside the microgrid. But what we need to do is the feeder needs to actually tell the microgrid what it needs to do. The feeder needs to be able to, give rules, if you will, to the microgrid that says, in an hour, I need you to absorb, 100 kilowatts of power that's on the feeder, because it's going to be too much and it's going to cause things to be unstable. So one of the things that we're going to have to do is we're going to have to basically build that bridge connectivity between both of those NATS buses. And we've got to be careful in how we architect that and how we do that, because things like the microgrid may be a customer-owned piece of setup. So it may be something that we have absolutely, from a feeder level, we have no visibility into the actual components that's inside of the microgrid. We have to basically know the capabilities of the microgrid as a whole and give it rules for operations. So we plan on making those that connectivity between those two different buses. Not exactly sure how we want to do that yet, but that kind of stuff will be coming once we start distributing all of the NATS bus across the feeder. Just show you a couple of little demos that we have done over the past few years. And DistribuTECH is one of the larger conferences that the power systems groups actually go to and the utilities go to. It occurs in the early part of the year every year. Well, back in late January of 2019, we did a demo in Sierra Wireless as booth. Sierra Wireless, they produce like a line of gateways, which are basically, cell modems that allow us to connect things across the grid. They, operate across a lot of different spaces besides just, power systems and utilities. But we have been working with them so that we can put distributed applications inside these gateways that have compute resources that are basically sitting there idle, that because the gateway is what's happening in it doesn't need all of the horsepower that's in that radio. So we're working with them, and we actually they put a Docker runtime inside this Sierra Wireless device, and we built one of our OpenFMB applications to talk to that meter that's right above it and get what that meter is seeing from a power usage at any given point. We were talking to that meter every second to say, okay, what's the power usage going on? So the polling is actually happening from inside this application to that meter. No outside system is actually polling it. And you can see around here, there was like 400 watt light bulbs. There was a little small heater down here that people could turn the lights on. They could crank the heater up, low, medium, high, and they could actually see pretty much what the real-time power out or power usage was across those. We were publishing data, again, once every second. Every time we would poll the meter, we would publish the data once a second, and it would send it out the cell modem. You'll see there's the radio antenna is right here, across through another cell gateway into this laptop, which would then there was applications that would subscribe to that data that's being run or being delivered. And you could see some of those real-time measurements would be displayed up here so that you could drill down into all of those different measurement data structures. That's part of our OpenFMB setup. But there was another subscriber that's sitting there and sticking all that data into a time series database, which Grafana wound up pulling out and being able to map out the energy usage or the over time. And as you can see here, you can see where people have been playing with turning the heater on and off, turning the lights on and off. You can see the power usage going up, and everybody was seeing about a 1.5 second delay between when something would happen on over on the rack on the left. They crank the heater up, and about a second and a half later you would see the graph change. And part of that is the polling rate that we were using. Part of it was the rate at Grafana. It would pull the data out of the database, but it was still pretty much fairly real time of what was going on. Well, at DistribuTECH this year, we did a little bit bigger setup where we kind of simulated an entire feeder with actual, some real grid level equipment. You can see some these blue compute nodes that you see here, some real actual controllers. There's a real controller over here that we actually use today. There's Sierra Wireless. There's one of their gateways there. There's another one there, devices from Cisco. So some of these real pieces of equipment we are actually distributing applications on, and we actually simulated a feeder and the operations of a feeder at DistribuTECH this past year. So what I want to do is just give you guys a quick demo of what's going on at the microgrid. Just wanted to show you guys a little bit about what's some of the data that's flowing around on our NATS message bus. Let me see yeah, it is still up and running, good. But you can see that, it's pretty much it's real time. We're polling, I think, or publishing data like once a second from inside the microgrid, and you can see all the different types of data. There's data from the switches, there's data from the meters, there's data from the solar, there's generation resources, but there's all of this data is actually being published onto our NATS message bus so that we can actually drill down and see what is actually going on inside of these devices in our microgrid pretty much in real time. Let me do a quick filter here so that we can actually drill down and just to show you guys a little bit more. And I'm going to subscribe to one of the switches that's actually in our microgrid, and you can see that data starting to come across now. So I'm only pulling in one particular switch. So as we drill down through that one instance or that one reading that I got, there was, 10,000 watts coming through that. So let's just watch that a little bit down here. And you can actually see pretty much, once a second, we can see the real-time data that's actually flowing from those switches. And all of this is being published from NATS software or that's we've written to get the data out of the switch and be able to publish it across NATS. And this is another C# application that's been interfacing with the NATS message bus and pulling all that real-time data back in. So let me, with that, of course, hang on, let's get back to where we were at. Go here. Here's just a couple of quick links. If anybody wants to learn a little bit more about the open field message bus and how we've done some of that, there's some sample applications that I put out there just so that you can kind of see how to interact with the OpenFMB data structures. Anybody wants to contact me, there's a whole list of contact information for me if you want to get in touch and have any discussions about some of this. That would be perfectly fine as well. And with that, that's all I have right now. So hopefully I stayed close to being on time.
Dwayne, this is Derek. Thank you so much. I remember when we first started talking, I shared a passion with modernizing some of our infrastructure, right? The utility grids, the electrical infrastructure, the notion of smart cities, and how if we could, NATS could play a small role in kind of enabling that push-based telemetry data, understanding, collecting more data, and of course the control system. So really, really appreciate the time you spent with us. It's really, really fascinating, and look forward to continuing trying to be a part of the solution. So
yeah, NATS has worked out extremely well for us, and we've been very, very pleased with it so far. It's all the things that you guys have added into the version 2 releases and stuff from the security standpoint. That's been very good, and we're definitely planning on taking advantage of a lot of that as we go forward.
Yeah, thank you. I really appreciate it.